In this video, we will review some basic math topics that are useful in your studies for the Physics 1 series. We'll start with a discussion of angles. There are a number of common geometries that appear in physics problems. We'll start by considering the geometry of complementary angles. The crossing of two perpendicular lines forms a right angle, or a 90-degree angle. We typically show this by overlaying a small square inside the angle that is 90 degrees. Two angles that add up to 90 degrees are called complementary angles. Another way to say this is that two angles that together will fill a right angle are complementary and therefore sum to 90 degrees. That means if you see a geometry in which you know one of the angles that fill this 90-degree crossing, then you can calculate the other angle of interest by taking 90 degrees and subtracting the angle that you know. For example, if we know that angle alpha here is 25 degrees, then you can calculate this angle beta by simply subtracting 25 from 90 to get 65 degrees. The next geometry that we'll look at is the geometry of having supplementary angles. Two angles that sum to 180 degrees are called supplementary angles. One way we see this is that the two neighboring angles that are formed when two straight lines intersect are supplementary and add to 180 degrees. In this case, the angle labeled alpha and the angle labeled beta formed with the crossing of these two straight lines sum to 180 degrees. This, of course, means that if you know the angle alpha, but don't know the angle beta, and you see this geometry, then you can calculate the angle beta by simply taking 180 minus the angle alpha. Again, as an example, if alpha is 25 degrees here, then the angle beta would be calculated as 180 minus 25 degrees, which gives you 155 degrees for angle beta. The third common geometry you will see is, again, having two intersecting lines, and you are interested in the opposing angles formed by these two straight lines. In this geometry, the two opposing angles are always equal to each other. So if you know one angle over here, you automatically know the other angle to be equal to that one. There are actually two sets of opposing angles formed whenever you intersect two straight lines, and so this angle here is automatically equal to that angle. Finally, the last geometry we'll consider is when two parallel lines are both intersected by a third straight line. In this case, there will be sets of corresponding angles that are formed that are equal to each other. Specifically, this angle and this angle, these interior angles, are going to be equal to each other. So this angle will equal to this angle. And you can partly see why this is from the geometries we've already looked at, because we know that this angle is equal to its opposite angle, so this would also be alpha, and that this angle, by symmetry, since these two lines are parallel and this is the same line, must equal to this one. Of course, there's other sets of corresponding angles, shown here in magenta. This angle corresponds to this angle, and so they are both equal to each other. Our next topic will be an introductory review of vector addition. Specifically, we'll be looking at the graphical head-to-tail method. We'll start our review of vector addition by defining what a vector is. A vector is a quantity that has both a magnitude and a direction. It can be represented graphically by an arrow that is drawn so that it points in the direction of the vector quantity and has a length that's proportional to the magnitude of that vector quantity. For example, map directions are commonly represented as vectors. The direction 10 meters north would be represented by an upward pointing arrow, while the direction 10 meters to the east would be represented by an arrow pointing to the right that has the same length as the arrow pointing upwards for 10 meters north. Note that these two directions would get you to very different places if you started at the same location. So they are very different quantities, even though they have the same length. they have a different direction, and that makes them distinctly different vectors. 14 meters northeast would be represented by a diagonal arrow pointing up and to the right. That would be 1.4 times as long as the length of the 10-meter arrow. In physics, we prefer to represent the direction with an angle. By convention, the angle is 0 degrees when pointing straight to the right. Angles are then represented as being positive as you move counterclockwise around the circle. So 90 degrees would point straight up, 180 straight to the left, 270 straight down, and 360 would bring you right back to straight to the right. And so in physics nomenclature, these map directions would be denoted by a magnitude and an angle. Next, let's consider how we can add two vectors together using a graphical method. Vector addition must account for both the direction and the magnitude of the vectors to be summed. So if we have two vectors that we wish to add together, we would sum these two vectors graphically by translating the second arrow so that its tail sits at the head of the first arrow. By translate, we mean to slide it without rotating it. If we do this, then the vector sum is then represented by the resultant arrow, r, which points from the tail of the first arrow to the head of the second arrow. Similarly, we can handle vector subtraction as a special case of vector addition. Recall that subtraction can be written as a minus b is the same as a plus the negative of b. This we do in algebra all the time. The same is true for vector addition. To utilize this method, we need to understand what it means to have a negative vector. The inverse of a vector, or negative vector, has the same magnitude as the original vector, but points in the opposite direction. So if we want to subtract vector b from vector a, what we do is we graphically invert the vector by flipping it by 180 degrees. We can then add the inverted vector to the first vector using the same head to tail graphical method to give us a resultant vector that goes from the tail of the first to the head of the second vector. Now that we've defined the vector, let's go back and consider angles again, this time in the context of the unit circle. There are two ways that angles are often reported. One way is to measure angles in degrees, and another is to measure angles in radians. Although we're more familiar with measuring angles in degrees, the radian is really the more natural unit for measuring angles when you're dealing with angles in a circle. Let's consider a circle with a radius of r, as shown in the figure here. Right? If we take that length r and trace it along the arc of the circle's perimeter, then the angle that's swept out by that length r along the perimeter will end up giving you the angle of exactly 1 radian, where 1 radian is roughly 57.3 degrees. A full circle, which by definition is 360 degrees, therefore works out to be exactly 2 pi radians. Let's think of that unit circle as a clock face, where the clock arm rotates counterclockwise around that circle. If the arm length is defined as having a radius of 1, then the tip will trace out a unit circle. If we illuminate the clock from the side, the vertical shadow of the clock arm changes its length sinusoidally as the arm rotates. Similarly, if we illuminate from above, the arm's horizontal shadow changes its length sinusoidally as the arm rotates as well. Let's define 0 degrees on the unit circle as pointing straight to the right, as we previously mentioned, and positive angles as running counterclockwise starting from 0 degrees. Let's trace out these shadows on a running strip of paper as the angle goes from 0 degrees around the unit circle to 360 degrees. Notice that the vertical shadow tip starts at 0 for 0 degrees. Right? The shadow is right here. On the other hand, the horizontal shadow starts at +1 for 0 degrees. As we trace these out, you see that the vertical and horizontal shadows trace out a sinusoidal curve. The vertical shadow tip is described by the function y is equal to sine of the angle theta, while the horizontal shadow tip is described by the function x is equal to cosine of the angle theta. Let's consider a situation where we rotate to an arbitrary angle on the unit circle. And let's take a closer look at the horizontal and vertical projections. Let's extrapolate this to a vector of arbitrary length as well as an arbitrary angle. The horizontal projection of this vector is given by r cosine theta. The x component of this vector is given by the horizontal projection or shadow of this vector is given by x is equal to r cosine theta, while the vertical projection or vertical shadow of the vector is given by y is equal to r sine of theta. These projections are also called the horizontal and vertical components of this arbitrary vector. From this, you can see that the trigonometric functions, sine, cosine, tangent, can be written in terms of the sides of a right triangle formed with the angle theta. We can refer to the side of the triangle that is opposite the angle, or the side of the triangle that is adjacent to the angle. And of course, the slanted side of the right triangle is called the hypotenuse. In this way, the sine of the angle is given by the ratio of the opposite over the hypotenuse, while the cosine of the angle is given by the ratio of the adjacent to the hypotenuse. And then the tangent of the angle is given by the ratio of the opposite over the adjacent. Now that we've reviewed the trigonometric functions, let's go back and look at vector addition again. This time we will tackle vector addition using an algebraic method called the vector component method. To utilize the vector component method of vector addition, we first need to break down the individual vectors into their components. So consider a vector A oriented at some angle theta relative to the horizontal. Remember, positive angles are taken to be counterclockwise from the positive x-axis. The x component of the vector A is given by the cosine formula. Ax is equal to the magnitude of A times cosine of theta. The y component, Ay, of the vector A is given by the sine formula. Ay is equal to magnitude of A times the sine of the angle. As an example, if the vector A had a magnitude of 6 meters in length and was at an angle of 60 degrees with respect to the horizontal, then our formula would give us that the x component of the vector A is 6 meters times cosine of 60, which gives us 3 meters. Similarly, Ay, the y component of the vector A, is found from multiplying 6 meters times the sine of 60 degrees. Sine of 60 degrees is roughly 0.866, which gives us a final answer of 5.2 meters for the y component. Let's consider two vectors, vector A and vector B, whose angles are given by theta A and theta B relative to the horizontal. and whose magnitudes are given by the absolute value of A and the absolute value of B vector. Let's calculate the vector sum. To get the resultant vector, we can, of course, use the graphical head-to-tail method we described previously, or we can use the vector component method. So let's take a closer look at this vector component method. To use the vector component method to add vector A to vector B, we first start by finding the x and y components of both the A vector and the B vector using our sine and cosine relationships. So for the A vector, we get the x and y components from the cosine and sine formulas. Similarly, for the B vector, we get the x component and y component of the B vector using its magnitude and its angle. And then, to find the components of the resultant vector, we simply sum the x components of A and B to obtain the x component of the resultant vector. Similarly, we can add the y components of A and B to obtain the y component of the resultant vector. This, of course, forms a right triangle with Rx and Ry being the sides of the triangle, and the resultant vector itself lying along the hypotenuse. And so we can use Pythagorean's theorem to find the magnitude of the resultant vector. Remember that the tangent of the angle is equal to the opposite over the adjacent, or in this case, Ry over Rx. And so we can find the angle by taking the inverse formula, or the arctangent of Ry over Rx, to give us the value of the angle that we're looking for, specifically the angle that the vector r makes with respect to the horizontal axis. Let's work through an example real quick. If A has a length of 6 meters and makes an angle of 60 degrees above the horizontal, while B has a length of 10 meters at an angle of 15 degrees above the horizontal, then let's calculate the result of adding A plus B using our vector component method. First, we find the x component of the A vector by using the cosine formula. Plugging in the numbers, we get 3 meters. Next, we can use the sine formula to find the y component of the A vector. Again, when we plug in the numbers, we get 5.2 meters. We do the same thing for the B vector. Plugging in the numbers, we get Bx is equal to 9.66 meters, whereas By, using the sine formula, gives us 2.59 meters. Now that we have the x and y components for both vectors, we find the x component of the resultant vector by adding just the x components of the two vectors. Plugging in our results, we get 3 meters plus 9.66 meters, gives us 12.66 meters for Rx. Similarly for Ry, we sum the y components of A and B to give us 7.79 meters. Our next step is to use Pythagorean's theorem to calculate the magnitude of the resultant vector. Plugging in our numbers, we get a final answer of 14.86 meters. And finally, we use our arctangent formula to figure out the angle that the resultant vector makes with respect to the horizontal axis. Plugging in our numbers, we get an answer of 31.6 degrees. Next in our review, we'll take a look at algebraic equations. We'll start by looking at the concept of proportionality, also known as scaling. Scaling describes how one quantity changes in response to changing another quantity by either multiplication or division. The first type of scaling we'll look at is called linear scaling. Proportionality describes situations where two quantities scale linearly. One way this can happen is with direct proportionality. What this means is when one quantity doubles, the other quantity doubles. An example of this from real life: if the price of gasoline increases by 25%, then the cost of filling your 10-gallon gas tank will also increase by 25%. And of course, if the price of gas doubles, then it'll cost you twice as much to fill the tank. Another type of proportionality is inverse proportionality. When you have inverse proportionality, when one quantity doubles, the other quantity is cut in half. A simple example of this is if you triple the number of friends that you invite over to share your cake at your party, then you'll have to reduce the size of the cake slice for each guest to 1/3 in order for there to be enough cake for everyone. Mathematically, the expression for direct proportionality is y is equal to kx, whereas the expression for inverse proportionality is y is equal to k times 1 over x. The symbol k is just a number, often called the proportionality constant. Another type of scaling that appears commonly in physics classes is quadratic scaling. Quadratic scaling describes a situation where a change in one quantity by a certain factor causes another quantity to be increased by that factor squared. For example, if you were ordering a square dance floor to be installed for a party, if you triple the length of the square-shaped dance floor that you want, you will increase the area of the floor by a factor of 9, because of course 3 squared is equal to 9. The mathematical expression for quadratic scaling is y is equal to kx squared, where again k is that proportionality constant. It's just a number. Why is scaling important? Understanding how variables scale in a physics equation helps us to understand how physical quantities are related to each other, which is an important step in developing an intuition for cause and effect in physical systems. Let's take a physical example. Here's an equation that describes the motion of a hockey puck on a frictionless surface like an ice rink. D stands for the displacement, how far the puck moves. This symbol V0, or V0, is the initial velocity. It's the start speed. How fast is the puck moving to start with? T is just the time. How long do you push the puck for, or how long do you observe the puck being pushed for? F is the amount of force that you apply onto the hockey puck. And M is the mass of the hockey puck itself. If we substitute the symbols in the equation for their meanings, we get something that might be a little easier for a beginning student to understand. Let's consider some special limiting cases of this equation. Let's start by considering a scenario where we don't push the puck at all, but that it does have a starting speed at the beginning of the experiment. The equation then tells us that if we apply no force, then if we wait twice as long, making time our variable, then the puck will move twice as far if we keep the starting speed the same. In this scenario, the starting speed is a constant. That is our proportionality constant, k. And we have an equation that says that the observed quantity is equal to a proportionality constant times the quantity that we change. This is a direct proportionality equation. And so if we wait for twice as long with the same starting speed, then the puck will go twice as far. On the other hand, we could take the same equation and set the time that we observe the puck for to be unchanged. In that case, this becomes our proportionality constant, and our equation becomes how far the puck goes is equal to a proportionality constant times the starting speed. And if we change the starting speed while keeping this proportionality constant of how long the same, then we again have a direct proportionality equation. And so if we double the start speed, we'll double how far it goes. And if we have the start speed, the puck will move half as far in that same amount of time. Let's consider a different limiting case where the puck starts with 0 velocity, that is, it's at rest, but we do push on it. So if we start from rest, then if we push twice as hard, but leave everything else the same, so that how long we observe it for and how long we push it for doesn't change between experiments, and how heavy the puck is doesn't change. The only thing we change is how hard. If these are now constant for our experiment, this becomes our proportionality constant, how long squared over how heavy. Our equation then tells us that we have a linear proportionality between how far the puck will move and how hard we push it, with this being the proportionality constant k. So if we push twice as hard, the puck will go twice as far in the same amount of time, and assuming the puck does not change its weight. Instead, we could change how long we push the puck for. If we don't change the force and we don't change how hard the puck is between different experiments in this scenario, then this ratio becomes our proportionality constant k. And our equation now tells us that we have a quadratic scaling of the observed variable is equal to a proportionality constant times our changing variable squared. And because of that squared factor, if we wait twice as long, the puck will have moved 4 times as far. Finally, we could choose to make the puck twice as heavy, in effect changing how heavy the puck is while leaving the force and how long we apply the force for unchanged, so that this set of terms up top becomes unchanged or constant, and thus our proportionality constant. And we now have an equation that says how far the puck will go is equal to a proportionality constant over the variable that we changed. That's an inverse proportionality, and that tells us if we double the mass of the puck will move only half as far, assuming we've pushed with the same force for the same amount of time. Next, let's review a few strategies for solving algebraic equations. There are a number of different methods for solving for a variable of interest, including rearranging the equation, substituting one equation into another, or combining different equations together with mathematical operations. We'll look at all three in turn. We'll start with rearranging a single equation. We can rearrange a single equation by several different operations. We can add or subtract the same value from both sides of the equation. For example, if we have an equation that says y plus 3 is equal to 9x, and we're interested in solving for y, we simply subtract the 3 from both sides in an effort to get the variable of interest by itself on one side of the equation. We can also multiply or divide the same value from both sides of an equation. So if we have an equation that says 8y is equal to 3x, and we are again trying to solve for y, in an attempt to isolate the y by itself, we multiply both sides by 1/8, or equivalently, you can say we divide both sides by 8 to yield an equation that says y is equal to 3/8 x. And of course, we can apply any sequential combination of these operations. For example, if we have a formula that says f times parentheses y plus d is equal to u, and we want to solve again for the variable y, then our strategy is to isolate y by working from the outside in. So we'll start by removing the f from this side of the equation in an attempt to isolate y. And to do that, we would divide both sides by f to yield an equation that says y plus d is equal to u over f. To finish the isolation of y on the left-hand side, we're going to then subtract d from both sides of the equation to yield a final equation that says y is equal to u over f minus d. The next method we'll look at is to use substitution to solve a system of two or more equations. We can solve a system of equations by substitution to solve for a variable of interest in terms of the other known variables while eliminating undesired unknown variables. For example, if we are given two equations, y is equal to x plus 2t, and another equation, y is equal to 4x minus t, and we're told that both of these equations apply at the same time, then what we can do to solve for y in terms of only the known variables, in this case x, and also of course constants, is we will rearrange one of the equations to isolate the undesired variable. Now there's two ways we could do this. We can add t to both sides to give y plus t is equal to 4x. That makes sure that the t comes in with a positive sign. And then we can isolate the t by subtracting y from both sides. This leaves t by itself on the left-hand side and 4x minus y on the right-hand side. Alternatively, we could have isolated t by simply subtracting 4x from both sides to get y minus 4x is equal to minus t, and then divided by minus 1 to get positive t is equal to 4x minus y. What we then do is, now that we have an expression for the undesired variable, the one that we have no information on, we can substitute this value of t into the other equation for the t there. When we do this, we end up with an equation that says y is equal to x plus 2 times, and then for t, we substitute in the 4x minus y. Our next step is then to distribute the multiplication of 2 through these two terms. The idea is to, if at all possible, end up with simple isolated terms that we can add and subtract. So we distribute the 2 through, and we get y is equal to x plus 8x minus 2y. Next, we move all the like terms onto the same side of the equation. So we have a y over on this side and a y over here. We have an x and an x. Let's move the 2y over to here by adding 2y to both sides. So now we have y plus 2y is equal to x plus 8x, and then of course minus 2y plus 2y cancel to 0. We can then combine these terms. Y plus 2y is 3y. X plus 8x is 9x. And then dividing both sides by 3, we end up with our solution, y is equal to 3x, where we now have our variable of interest in terms of our known variable, and we've eliminated the unknown variable, the undesired unknown variable. Another method we can use to solve a system of equations is to combine equations, and we can combine them with a number of mathematical operations: addition, subtraction, multiplication, or division. We'll use the same example, but use a different method to solve it. We again have two equations that apply simultaneously. Y is equal to x plus 2t, and y is equal to 4x minus t. What we'll do is we'll multiply both sides of the bottom equation by 2 to turn that equation into 2y is equal to 8x minus 2t. The rationale for doing this is that we can then combine it with the original top equation, and the undesirable unknown variables will cancel out. In this case, the positive 2t in addition to the minus 2t will combine to equal to 0. And we are left with 3y is equal to 9x plus 0t. This, of course, simplifies to 3y is equal to 9x, which we can divide both sides by 3 to give our solution yet again, y is equal to 3x. For our final topic, we'll review some concepts from basic calculus, including derivatives and integrals. Up to this point, we've been dealing with algebraic equations. Algebraic equations help us describe the value of one quantity in the system as a function of the value of another quantity in the system. But in science, we're often interested in studying how things change or evolve. Calculus is the mathematics of how a quantity is changing. Derivatives describe the rate of change of a quantity's value and is equivalent to the slope of a plot of that quantity. Integrals are the inverse of derivatives in that they describe the accumulation, or sometimes the depletion, of a quantity due to its rate, and is equivalent to the area under the curve of a plot of that rate. Let's take a look at derivatives first. Consider the artificial data shown for a tumor volume versus time. In this plot, we have time on the horizontal axis and the tumor volume, which we've labeled f, which is a function of time, on the y-axis. The average rate of change in the tumor volume between years 0 and 6 can be found as the change in the volume from the endpoint to the starting point, divided by the duration of that observation. In this case, we're taking the difference in the volume at time 6 and the volume at time 0, and dividing that by the difference in time from the start to the end of the observation, in this case, 6 years. The change along the vertical axis of a plot is often referred to as the rise, while the change along the horizontal axis of a plot is often referred to as the run. The average rate, as described by this equation, is equal to the slope of the associated triangle of this plot, where the triangle consists of the run, the change in the horizontal axis on one side of the triangle, the rise, or the change along the vertical axis on the other side of the triangle, and the slope being equal to the rise over the run. But as you can see, the average rate, which is the slope of this large right triangle, may not accurately reflect the true rate at every instant, as drawn here in this orange curve. In this case, the average slope overestimates the true slope at both the early times and the late times, where you can see the purple hypotenuse has a much higher slope than the local slopes shown in the dashed green line. At the same time, we see that the average slope in this plot underestimates the local true slope in the intermediate years. So if we wish to determine the true rate of change at year 3 more accurately, what we're going to need to do is we're going to calculate the average rate over a shorter period of time. Rather than looking from year 0 all the way to year 6, we'll take a shorter interval of time around year 3. For instance, we can look just between years 2 and 4 and evaluate the tumor volume at year 4 and year 2. And again, using rise over run to calculate the slope, we can get the average slope or the average rate of change of the tumor volume between years 2 and 4. Calculating the average rate over a shorter period of time provides a more accurate estimation of the true instantaneous rate for any instant in that time window. And as you can see, this shortened time window gives us a better approximation of the true slope at the 3-year time point. In the limit that we shorten the time window to be infinitesimally small, we can obtain an exact determination of the instantaneous rate at that point in time. Mathematically, we say that the average rate is the difference between the function over a time window divided by the duration of that time window, or more concisely, delta f over delta t. We then take the limit as delta t approaches 0 to get an infinitesimally small time window. In this limit, the difference ratio on the left becomes a derivative of f with respect to t, as shown on the right. And that derivative is equal to the instantaneous rate of this function at this particular time point. If the data can be fit with a mathematical function, say f of t, then the instantaneous rate of change can be found by taking the derivative of that function df dt. Now, in the case we just discussed, the quantity of interest varies as a function of time. That was the tumor volume growing. But we may also be interested in quantities that vary as a function of position, which would be written as f of x. For example, f of y could represent the variation of the salt concentration in seawater as a function of depth in the ocean. In that case, the rate of change of salt concentration with depth would be found by taking the derivative of that function with respect to y. So far, we've talked about quantities that vary only as a function of one variable, either as a function of time or as a function of space. A quantity that varies with both time and space simultaneously will require evaluation with partial derivatives rather than total derivatives. The use of partial derivatives is beyond the scope of this tutorial and unlikely to appear in the Physics 1 series. Let's look at the derivatives of some common math functions. If f of x is cx, where c is just some constant value, then the derivative df dx is just that constant value. If the function is cx squared, we find the derivative by bringing the exponent down and then reducing that exponent by 1. This gives us the derivative of cx squared to be 2cx. If the function f of x is equal to c over x, we can rewrite this as c times x to the minus 1, remembering that x to the negative power is the same as 1 over x to the positive power. We can then repeat the procedure of bringing the exponent down and reducing the exponent by 1, which then results in the derivative of c over x as being minus c over x squared. Generalizing this process for a function cx to the n, where n is any number, we simply bring that number down and reduce that exponential number by 1 to give us that the derivative of cx to the n is n times cx to the n minus 1. If f of x is just a constant, we remember that x to the 0 is the same as 1, and we can always multiply any number by 1, so we can write c as cx to the 0. If we repeat the procedure of bringing the exponent down, then we end up with a 0 out front, and 0 times any number is 0, and that tells us that the derivative of a constant is always 0. Finally, we can go back and use a similar trick, and whereas x to the 0 is 1, x to the 1 is x. Finally, we can go back and evaluate the derivative of cx using a similar trick. Whereas x to the 0 is 1, x to the power of 1 is just x, which means that we can purposely rewrite x as x to the 1, and then repeat the procedure of bringing the exponent down and reducing that exponent by 1. But x to the 0 is 1, so we can get rid of both that 1 and that 1, and we're just left with c. Some other derivatives of common functions include the derivative of the exponential e to the x. Turns out that the derivative of e to the x is just e to the x. Similarly, the derivative of a constant times e to the x is just that same constant times e to the x. On the other hand, if our function is c e to the kx, where k is yet another constant, then calculating the derivative involves bringing down that k while leaving the rest of the expression unchanged. So the derivative of c e to the kx becomes k c e to the kx. Finally, let's take a look at the derivative of some trigonometric functions. The derivative of sine of x is just cosine of x. If we place a constant in front, that constant just carries over. So the derivative of c sine of x is just c cosine of x. If we place a constant inside of the sine, that constant gets replicated outside when taking the derivative. So that the derivative of c sine kx becomes k c cosine kx. The derivative of cosine is minus sine. If we multiply the cosine by a constant, that constant carries over, so that the derivative of c cosine x is equal to minus c sine of x. Again, if we place a constant inside of the cosine, that constant gets replicated on the outside in the derivative. So the derivative of c cosine kx is minus k c sine of kx.